Thank you very much indeed for your very warm welcome. I want to take you back today, and hopefully bring you back again, to Greece, to 100 years BC. Now, for those of you who've come a little dusty in your remembrance of history, one or two of the older professors who may or may not remember the times, 100 BC was a time of change in the ancient world. The glorious era of Greece was past. The real golden age of Greece was about a few hundred years in the past. Greece was still a nice place to live, but there was no doubt there was a new kid on the block. The Romans, by this time, were conquering all around the Mediterranean. The empire had not been declared yet. That was another 50 years or so in the future. But there's no doubt that a new civilization was taking over. And it's from this sort of era between the great Greek civilization and the great Roman civilization that the artifact I'm going to talk about comes from. And it was found in a shipwreck, and just a little bit of geography. How many people have been on holiday to Greece? Okay, you pay them far too much, these students. Anyway, they work their passage. Anyway, let's see, who's been to Crete? Okay, there's Crete. Who's been to Athens? That's Athens up there. Who's been to Rhodes? Much less likely. A few. Excellent. Okay. So Athens, Rhodes, Crete. You've got the sort of place where you are. Okay. Here is an island called Kythera. And across the straits from Kythera is an island called Antikythera, opposite or in front of Kythera. Hence the name. Because what happened was, oh, don't worry about these. It's something wrong with my laptop, and it's not worth me trying to fix it. Nothing's going to blow up in the next half hour. It's just the Martians trying to. Anyway, some sponge fishers who lived in Simi were on their way to their sponge gathering grounds, which were on the coast of North Africa. They were sailing across to North Africa to go for their season's sponge diving, when a storm blew up. Now, the Mediterranean is often thought of as a nice, quiet sea. In fact, it's very dangerous because some storms can blow up very quickly and unannounced, and they can be very violent. So they sheltered in the lee of the island of Antikythera for the storm to blow itself out. When the storm had blown itself out, they decided they would dive. Now, whether this was to get some sponges or get some clams for lunch, we don't know, but they dived, and shortly afterwards one of the crew came up brandishing a bronze arm and saying, "There's a shipload of maidens down there." Well, when they'd calmed him down, what they dived again and they had found the wreck of a Roman era trading ship, and it's from that wreck that this artifact I'm going to talk about came from. Now, for the next couple of years, there was what was really the first ever proper underwater archaeology expedition mounted by the Greeks, the ministry and the museums. And here's a picture from May 1901 on one of the recovery ships. And can you see this lump here? Okay. Well, that, in fact, is that. This shipwreck contains some of the finest known Greek classical era bronzes. It contains statuary, marble statuary, and even fine glassware. So that could almost be Rennie Mackintosh from Glasgow, couldn't it? But this is stuff from around 100 BC and earlier. Superb stuff. This was all taken back to the National Archaeological Museum in Athens, where it remains to this day. And there's a splendid exhibition on at the moment, if you happen to be in Athens, to go and have a look at. Now, also in this stuff came up a lump of bronze. My guess is that they probably thought it was something like a head of a statue or something. And it was only later in the museum, a few weeks later, that it cracked open, probably through drying out, although we don't know if somebody hit it with a hammer. Anyway, it cracked open. And a visitor noticed that this lump of bronze had gear wheels in it. Now, gear wheels were not known. Precision metal gear wheels were not known from antiquity at that time. Now, to give you some idea, it's now in many pieces. I'll show a picture of all the different pieces that it's in a minute. This is the largest remaining fragment, and that is a model of it to scale. So that's the size of that fragment there. And I think you'll see, if you look carefully, can you see a gear wheel here? A gear wheel here, there's another gear here. And in fact, this big wheel here itself has teeth on it and is a gear wheel. Now, I'll refer to this wheel as the chariot wheel. Now, of course, it has nothing really to do with chariots, but you know what I mean, and it'll be a convenient way for us to remember. It's quite important in the actual way the mechanism functions. The real implication of this mechanism really wasn't known until the 1970s or so, at the beginning of end of 60s, 1970s, when the first radiography of the fragments were known that allowed people to were done, which allowed people to see the number of gear wheels within these remaining fragments. Now, in this fragment, the X-ray and also other kinds of radiation investigation showed that in the mechanism there survive 30 gear wheels. And the original mechanism must have had more than that. Now, to put that in context, 30 gear wheels, there is nothing as complicated as that in terms of gearing until the era of the medieval cathedral clocks, well over a millennium later. So this mechanism is quite extraordinary in its complication. And it was really in the around 2000 that, following in fact a student project on this, that we put together an international team to apply modern imaging methods to the remaining fragments to see if we could work out what the true structure and function of this device was. I won't get into the details of how it was put together. There are various people involved, as you can see here, people from the UK, from Greece, University of Athens. There were people from the Archaeological Museum in Athens. There were also 2 industrial companies which freely gave their time and equipment. That's a company called X-Tech, now part of Nikon Metrology, and Hewlett-Packard in Silicon Valley in the United States. I won't go into the details here. I'll just mention that some of these people, there's an Agamemnon and a Xenophon in here, which I think sort of gives a sort of air of authority, at least, to the historical investigation. And we were grateful for some funding essential funding from the Leverhulme Trust during the work. Here are some of the mug shots of some of the people involved. I'll just do this so that you can, if you see them in the streets, you can avoid them. Okay. Now, before we started work, there is a long history of work on the Antikythera mechanism. 2 people I'll mention in particular. One is an English but became American scholar called Derek de Sola Price, who did a lot of work on this mechanism in the 1950s, 60s, and 70s, and in fact wrote a book that becomes really the sort of Bible of studies of this, initial Bible of studies on it, called Gears from the Greeks, which he published in 1975. He did a very great deal of the initial work, and with Caracalos did the first X-rays. And I'll also mention a guy called Michael Wright, who you may see on TV programs, delightful, eccentric character, who was a curator of mechanical engineering at the Science Museum for many years, and he's had very many interesting mechanical insights into how things work, which have been absolutely invaluable in decoding how the thing works out. Okay, well, as well as the main fragment I showed you, there are other fragments, as well as being the first known precision gear wheels, this thing also has the first known scientific scales. That's the size of that fragment there. And you can see it has scales on it, scientific scales or dials. And they're quite complicated. They're not simple dials, as you can see. In fact, you can see here 5 in a row. In fact, it's a spiral scale. So the first known scientific scales as well. Here's another fragment, cruelly enlarged. Okay, the actual fragment size is that. Okay. Now, if you look at it, you can see 2 things here. One, you can see the scientific scale. Can you see here? Nicely divided. Okay. But also you'll notice that there's a bronze sheet overlaying it on which there is a lot of writing. I don't know if you can see it in Greek script. And this is very helpful or interesting that the actual mechanism comes with some sort of, not instruction book, I think that would be too complicated a way to describe it, but a sort of specification. You know, when you get these things from Apple or whatever these days, it has in 15 languages telling you all the things you don't want to know about the mechanism. Well, this one has a sort of specification which does in fact tell you quite a lot, probably about what the mechanism was intended to do. They're the remaining 82 fragments. Some of them may or may not have anything to do with the actual mechanism. There are odd pieces that may not be. One or two have just got a few letters on. The main fragments are these ones here. This one has, as I've mentioned, 28 gears in. This has 1 gear in, and I think it's that one also has 1 gear in. So 30 years surviving. Now, how am I so sure about the date of this mechanism as 100 BC? I'll just rip through this quickly. First of all, there are coins on the shipwreck, and they're particularly some coins from Pergamon in the eastern Mediterranean, and we believe they were minted around 86 to 60 BC, so presumably they had to be minted and on the ship before it sank. So that gives you some sort of earlier state for the shipwreck, around 60 to 80 BC. The timbers of the ship are around 200 to 40 BC. That's a recalibration of the carbon 14 dating, and that's a pretty secure date now at 85% probability, so that fits in about right, that's okay. The epigraphy on the mechanism, that's the form of the letters. The form with which the letters and the words are put together changes in the Greek world. Over a period of about 30 or 40 years, there's subtle changes. The epigraphers, that's a useful word for Scrabble, epigraphers are the guys who look at the form of these letters and are able to tell you how old it is. They say that the writing on this mechanism is very characteristic of the late 2nd century BC, so just before 100 BC, or around there. Right, now we should work. Yes, okay. My apologies. Okay, now what does the thing look like? It's about this size, the size of a shoebox. Okay, about the size of a shoebox. And on the front, there would have been some sort of door or plate to protect it, covered in inscriptions. Then there'd have been a front face with a double dial on, with a pointer, and we know this because it mentions in the inscription about there being a pointer with a little golden sphere on, to illustrate where the sun is. A pointer showing the position of the sun in the zodiac. Remember, the sun moves around the sky during the year. That's what gives rise to your birth sign. Okay, if you're, how many Aries have we got here? About a 12th of the audience. Yes, Aries? Nobody's admitting they even know their birth signs, are you lying lot? Anyway, you know, your birth sign is where in the zodiac the sun was at the time of your birth. And so that goes around once a year, equivalent to once a year, to show where the sun is in the sky. There'd have been a pointer too to show the position of the moon in the sky around the zodiac. And also a little device, a half-silvered ball, to show what the phase of the moon was. Okay, and that's something that's been reinvented many times over history. Leonardo da Vinci did a design, and you've seen it in many clocks, I'm sure, as well. On the back of the device, there were 2 large dials. Wasn't known really what the purpose of these 2 large dials were when we started work, but I'll describe that later on. And then another back plate, or black door, again with lots of inscriptions on. The first thing we wanted to do when we started work was to give the thing a complete scan to see if we could get all the surface detail, the faint writing and so on, mechanical details. And we did that by a technique invented by this guy called Tom Maltzbender. Here's a very clever bit of computing and invention. He worked for the Hewlett-Packard Corporation, and what he invented was this thing called polynomial textual mapping. It's a hemisphere, you can see the size there, hemisphere with 50 flashbulbs on, electronic flashbulbs. You put an electronic camera on the top, or an ordinary, digital camera on the top, a laptop, and some very smart software. And it fires off the 50 flashbulbs in succession. And if you've got an object underneath that hemisphere, fire off the 50 bulbs in succession, record the images into the computer, USB stick with all the images on, okay, put it into your own computer, and then it's as though in software you can hold the thing and move it relative to the light. So you can get different illuminations. Now, those of you who are Time Team enthusiasts, watch any of those programs on the TV, will know that if you want to see faint detail on a landscape, one of the best ways to do it is to go up in an aeroplane or a balloon or whatever at sunrise or sunset when the sun is at a very glazing incidence. And then you can see the lumps and the bumps very well. And this technique works very well on imaging outside stuff. Here, for example, you saw what the on one of the fragments how hard it was to read some of the original stuff. Can you see this? We sometimes call this the Isle of Wight fragment. Anyway, here you can see the writing quite nicely. And those of you who are Greek scholars will immediately have noticed that there are three numbers there. There we are, 76, 19, and 223. Now, the astronomers among you, if any of them, will have immediately recognized the astronomical importance of these numbers. Now, I have given this talk before to where some very, very distinguished astronomers have been present. And when I mention this about these numbers, somehow they develop an interest in the ceiling or what's going on out of the window. Because these are numbers which astronomers would have known well in the past, but aren't really known so much these days. And I'll just go through them very quickly because I think it'll help you understand how the mechanism works. 19. 19 years is the number of years in a thing called the Metonic cycle. Now, Meton was a Greek astronomer around 400 BC, and it's thought that he, possibly some others, introduced into the Greek world knowledge from the Babylonians. The Babylonians, for hundreds of years, recorded observations of the motion of objects in the sky. And they recorded them on these so-called cuneiform tablets. There are thousands of these in the British Museum. That's the sort of size and shape that a cuneiform tablet would be, like that. And there are thousands and thousands of these survive. A lot of them have sort of tax records and that sort of thing, how many oxen so-and-so earned on them. But also a long series of hundreds of years' worth of observation and working out of the cycles of the sun, the moon, and the planets. And 19 years is a very convenient cycle because the following thing. You may have noticed that there aren't an integral number of lunar months in a year. You know about lunar month, full moon to full moon or new moon to new moon. But if I say, well, when's the next full moon? You'd have to look it up because they don't fall on a given day each month because the months aren't commensurate with the solar year. It'd be really good if they were, wouldn't they? Because then you can have your barbecue on the 15th of July every year and know that it would be a full moon. But you can't. And in fact, in ancient times, it was in fact quite important to keep track of the lunar cycle because particularly, I know it's partly farming things, people wanted to know when to plant their crops and so on, but also religious ceremonies and civil ceremonies were often held at the new or full moon, so it's quite important to know when they were. Now, there's a useful cycle because 19 solar years, 19 years, corresponds to almost exactly 235 lunar months. Okay, now what that means is the following. What's the date today? 9th of June. And anybody know what the lunar phase is today? I forgot to look it up too. Anybody see the moon last night? First quarter, is it? Okay, so if it's on the 9th of June, it's the first quarter of the moon. Okay, well done, thank you. Now, if you come back in 19 years' time, on the same date, it will also be first quarter of the moon. Now, once you know that, you can fill in all the moons in between. Okay, and that's the Metonic cycle. Very, very useful for filling in the new moons. And in fact, it's still used as the basis for determining the Western festival of Easter. Still used for that purpose. Anyway, okay, so that's what that is. So immediately these numbers tell you that this has got something to do with calendars or astronomical phenomena.
That will be Monday as well.
Sorry?
That will be Monday as well.
Will it be Monday as well? I don't know. I hadn't thought about that. Well, yes, okay. That'll be a worked example for later. Okay. 76 is four of those cycles minus 1 day, because that's even more accurate. But we won't worry about that. Okay. 223. Anybody? Might just recognize it. 223 is the number of months, lunar months, in a Saros cycle of eclipses. What that means is if there's an eclipse 1 month, now it has to happen with either full or new moon for obvious reasons, because you've got to line up the sun and the moon and the earth. If you have, say, a lunar eclipse at one full moon, 223 months later, lunar months later, you'll have almost exactly similar type of eclipse, but shifted in time by 8 hours. It's again one of these cycles, the Juda commensurates of the orbits. So if you've got a table of old eclipses, you can predict when there's going to be a likelihood of eclipses occurring in the future. It's a neat way of predicting eclipses. So the fact that this thing had these numbers on immediately when this thing was discovered suggested that the thing had astronomical purpose. Now, as well as doing the surface imaging, we wanted to give the thing an X-ray body scan, basically, to get three-dimensional information out of it. Now, I wanted to just have a little bag, go to Athens, put the stuff in the bag, bring it back to the UK to X-ray it. Now, I never mentioned the word Elgin, I never mentioned the word marbles at all, but there was no way that this thing was coming out of the National Museum in Athens. So we had to take the machine to Athens itself. It took us 4 years, in fact, to get permission to do the work at all through the Greek government. And here's the machine, which was lent to us by X-Tech, and this X-ray firm in Hertfordshire, and it was driven down through Europe and then through the streets and into the museum in Athens in the early morning. And yes, we did measure the door before we started. Give you some idea of it's called a Blade Runner machine, give you some idea of its size. You can see a computer monitor here, which will give you some idea of its size. It weighs about 8.5 tons. Most of that weight is lead shielding, because it's a very high energy machine. It's the highest energy machine they had built, because we wanted to be able to penetrate through the remains of the metal. A lot of it's sort of calcified and salts these days, but we needed quite high energies to do that. So you wouldn't put your actual body in there, because I don't think much would survive. The machine was developed for doing things like looking at jet aircraft turbine blades and printed circuits and so on. Very useful technical machine. And here's one of our X-rays. Gives you very fine detail. But I think just seeing an X-ray may not really give you the idea of the value of having what's called X-ray tomographic data. So what I'm going to try and do here is if it works, can't guarantee that today, but I'm going to show you a video of going down through the same view as you just saw, but stepping down through the device as it goes on. And yes, indeed, it is fortunately working. Okay, it's a bit slow. Okay, I'll point out things to you as we dive down through it. Can you see what's just about to appear is the chariot wheel, and can you see the gear teeth there? So that is the big chariot wheel gear teeth. It's got a complicated shaft in the middle. As you go down, you'll begin to see here's the first gear wheel, here's another gear wheel, here's another gear wheel, here's another gear wheel. There's some sort of horseshoe-shaped spacer there. There's sort of some intermediate flat plate with bearings on, another horseshoe spacer, 2 gears here with some sort of pin holding a gear in, a big gear here, an even bigger gear here, in fact with 2 lines of teeth on it, and then some gears mounted on that gear, etc., etc. So can you get the feel? Once you've got something that allows you 3-dimensional structure, you're going to have a lot more luck, or be able to piece together much more what the relationship of the gears and their function is. Well, as soon as we got this data, one thing I wanted to do was to count the teeth on the gears, because if you can get the numbers, if you can get the ratios of the gears, you can hopefully get the function. Now, in fact, that's not trivial even in itself, because many of the gears are broken. You can see here's an example of a gear with bits missing. The teeth are worn. It's been under the sea for 2,000 years. And in fact, we believe that these gears were made by hand. So in fact, the teeth spacing is in fact somewhat irregular anyway because of the manufacturing process. But we were able to develop statistical methods where we basically based on angular measurements of where the teeth are and just doing basically least squares fitting to try and see what the best fit we could get for different numbers of teeth for the different gear wheels are. And it worked extremely well, in fact. And here are a list of the teeth on the gears. And in most cases, they're accurate to 1. In other words, that's the correct count. In 1 or 2 cases, it's plus or minus 2. In a couple of cases, it's worse than that. But on the whole, the counts are pretty well determined. You'll notice some interesting numbers here you might not have thought of. There's 38. Well, that's 2 times 19. Remember, we had 19 for the Metonic cycle. That's what the Metonic cycle is. 53. There are 2 53-tooth gears. Not what you'd think would be a particularly one you might expect. Why 53? Anyway, they're there. And 127 was known really before we started. That's a gear which would be known you would need for doing the lunar cycles. Okay, now here is our reconstruction of what the mechanism looked like and how it worked. I'll go through this very quickly. It takes about a month staring at one of these to sort of really be happy about how the thing works, so I'm not expecting great results. Basically, here on the side of the mechanism, you turn a knob to make this crown wheel turn. That's the front. If I just show a reconstruction here, can you see here's the front? I'll come back to this in a minute. A knob on the side is how you'd work it. You turn a knob to make the thing work. That knob turns a crown gear here, which drives the big chariot wheel. The one turn of the chariot wheel corresponds to 1 year. All right? 1 year is one turn of the chariot wheel. What happens then for the drives, come down here, I'll describe in a minute. There are these 3 gears here are missing. As you can see, there's probably been a little bit of bash that's taken them out of here during the shipwreck. But in order to reconstruct the device, we had to put these 3 gears back in. But it turns out that if you put the right size in, they do have the right number of teeth. So we're fairly confident that, well, very confident that those are just missing from the device. Okay, on the front, as I mentioned, it had the zodiac around here and showing where the sun and the moon were in the zodiac. It might also, as I'll say more later on, have had a planetary indication on the front as well to show where the planets were in the sky. Early on, we had some luck in discovering an inscription which read spiral divided into 235 sections. In Greek, you may be relieved to find, not English, which immediately alerted us to the fact, well, 235, anybody remember? Metonic cycle? Yeah. And it's mentioned spiral here. Well, just before we'd started work, Michael Wright, who I mentioned to you before, had realized that those back dials on the back of the mechanism weren't circular, they were spiral in form. So obviously spiral, 235 sections, there must be a Metonic cycle dial on the back there. And indeed, this is what the back would have looked like, or something like this, with a 5-turn spiral at the top and a 4-turn spiral at the bottom. Now, why a spiral? Well, as I say, this top one is going to be 235 divisions. Okay, I find it difficult to see the minutes on a clock these days, so I could easily overrun. Okay, 235 divisions is difficult to see. So what they've done in this laptop version is they've wrapped it round so that you can see the divisions more easily. There'd have been a pointer which would show which division you're looking at. Aha, you say, but how do you know which of the divisions to look at? In fact, the pointers survive. And here's a picture of one of the pointers seen from the side. Perhaps it's easier on this one here. And it's got a pin on the end of it. So in fact, the pointer goes into a slot. This spiral is in fact a slot cut into the bronze disc. And the pointer can pull out of the center shaft. So as it turns around, the pointer pulls across the disc, like an old vinyl gramophone record, if you remember, with the needle on. And you just look at the end of the pointer to see whereabouts you're supposed to be on the dial. Now, it's a nice little bit of design, that. Remember, I would remind you, we're in 100 BC, not perhaps what you might expect. Okay. So, and there's you can see the remnants of one of those spiral slots on that fragment. So the upper dial had a spiral with Metonic cycle in. Surprisingly, too, there was a little sub-dial up there as well, and I'll come back to that in a moment. Here's how that top one worked. There you are. You turn the handle on the side, it drives the chariot wheel, and you can see through the yellow here, the gear trains down to drive this guy on the Metonic scale, and a little sub-dial as well. Now, the little sub-dial is a little 4-year dial. It rotates every 4 years. Can you read that? Nemea. Well, Nemea was one of the Pan-Hellenic athletic games. In fact, can you read here, perhaps a little better? Olympia, yeah, it's got a dial on to tell you when to have the Olympic Games. Now, we were quite gobsmacked by this. Unfortunately, we didn't make any money, as we should have done from this, I'd have thought, with the Olympic Games, but there we are. It's got a dial that tells you about the 4-year cycle of the Nemean, the Isthmian, and indeed the Olympic Games. Some of these games are held every 2 years, some every 4 years. Now, what does this imply? A social function for this device? Whatever. We wonder, in fact, though, it may be, in fact, an orienting thing, because calendars varied all around the Mediterranean world. And so what this may have been is a way of people would know what games were happening each year, and it may be a way of saying, well, that was the year they had Olympics in, this was the year they had the Olympics, and that would have made people realise a bit better what year they were talking about. Anyway, it's interesting. On the lower dial, there are these funny hieroglyphic things, or glyphs as we call them. And in fact, we realised that those, in fact, were what implied whether there was going to be an eclipse or not. And it's 223 divisions around this dial, Saros cycle, and they'd inscribed them when, on the divisions, when you might expect there to be a possibility of an eclipse, either a lunar or a solar eclipse. Okay, now how do you drive that bottom dial then? We've seen how you drive the top dial. I don't know if you can see there's a great big gear here. I've sort of tried to outline it here. This is the back of the main fragment here. It's this thing here. It's a great big double-toothed gear, which we call the turntable gear. And it drives in the following way. We're looking from the other side. There's the handle turning thing. There's the chariot wheel again. It drives down here and through this very big turntable gear, driving onto there and off from there down to this dial down here. It's quite complicated and a bit clunky, you might think. You don't really need a huge gear like that. And to begin with, we thought, well, they're not very bright at doing these things, are they? Big mistake, as we'll see. Okay, and the reason it's a big mistake is for the next thing. If you look at this construction here, Michael Wright noticed that the four little gears mounted on this big turntable gear. And he noticed these two gears, they're very small, these gears, about this sort of size. He noticed that in one of them, there's a slot. Can you see this slot here? And in the slot, there is a pin. Now, why? Why do you have gears with slots and pins in? Well, imagine the following. Suppose you want to represent an irregular motion. And I won't go into the details, but the moon has an irregular motion. From night to night, it moves at slightly different speeds. How would you put that into mechanical practice if you wanted it to vary slightly, the motion from night to night? Well, how about the following? Here's a device. You bring in the drive on this yellow drivetrain here through a double shaft, and you turn this gear around and around. This gear drives this gear here, which on it has a pin, and the pin's sticky up and goes around and around. Above it, you mount a gear with a slot in, but you mount that gear slightly off-center from the gear below it. So what happens as that pin goes around and round? Sometimes it's pushing slightly nearer to the center, and sometimes pushing slightly further away from the center. So what's going to happen to the drive? It's sometimes going to go a little bit faster, sometimes a little bit slower. You pick off the drive with this other gear and then take it up to where you want it. Yes, indeed, it provides a quasi-sinusoidal variation of motion. Now that's not all, because these gears, here's the drive to the lunar thing over here, and it's to do with this lunar drive that it works. You drive down through this series of gears here, down, where it goes? It goes through here, through here, through here, through here, and drives this variable speed device. Then it comes back up through here and onto the front drive. Don't worry about the complications. The only thing is you'll notice that these variable speed device is mounted on that huge turntable gear. Now what the cunning people, I nearly used a more technical term then, these cunning people have done is they've mounted these gears on the big gear. And the reason is that the actual lunar variation doesn't occur at exactly the period of a lunar month. It's slightly different because the reason for the variation in the speed is the elliptical orbit of the moon, which they didn't know about elliptical orbits, but they knew there was a variation. That precesses, the orbit actually precesses due to the gravitational influence of the sun. So the period is slightly different, the variation is slightly different from a normal lunar month. And by mounting these gears, what would be called epicyclically, on this bigger gear, the variation is not merely at the right amplitude, but is also at the right period. They've deliberately done this. They've mounted this variable speed device on this other gear train in order to give you the correct period as well as the correct amplitude. It takes a long time to think about it, but I think you'll believe that having doubly interlaced gear trains with a variable speed device is pretty smart, and perhaps not what you'd have thought the Greeks were capable of. Okay, there's the shaft going up, showing it's a compound shaft. Okay, so what's important about the mechanism? It's based on Babylonian period relationships. The astronomy is perfect for the era we're talking about, okay? And the mechanical design is superb, and we really didn't have any idea that the Greeks had such a knowledge of detailed mechanical design. Okay, did it have planets in? Well, I'll zip through this, but the captions do, the inscriptions do mention Aphrodite, which is Venus, Hermes, and also stationary points, which are the places where planets move across the sky, move backwards, and then move on again, so-called retrograde motions as observed from Earth. And it's almost certain that it did. In fact, in some of the inscriptions, I don't know if you can read that on one of the inscriptions, Cosmos. And this inscription here shows that it's a list of the planets in the order that the Greeks knew about them, the ones they knew about then through visual eye observations. Almost certainly it had some representation of the planets on the front. But that bit, unfortunately, is lost. It was presumably lost in the shipwreck, alas. But people do reconstructions. Here's a couple of our group, Tony Freeth and Alex Jones, have put together a rather nice reconstruction here where they've put in extra gubbins, extra mechanism in order to do a full display on the front of the device. There's one gear we don't know where it goes in. I thought I'd just mention this, a 63-tooth gear, which we've no idea where it goes. So it may be part of the planetary mechanism. We don't know. Where was this thing built? Probably here. This is Rhodes in about 100 BC, not Manhattan. Okay. This is Rhodes. It was a highly technical naval port with a very, very good bronze casting industry. And also this is, as I mentioned before, where Cicero saw a mechanism like the Antikythera mechanism. So that's my best bet anyway of where the thing was built, sometime just before or around 100 BC. Now, should we really be surprised at the Antikythera mechanism? Okay, let's take a vote. Are you, those people who are surprised at this, raise their hands. Right, those who are not. The old cynics. Okay, excellent. Okay, thank you. Now, most of you are surprised at that, and that's the normal reaction is indeed that you're surprised that the Greeks could do this. But perhaps we shouldn't be quite so surprised. Here's some contemporary jewellery of the time. No trouble with the metalworking. They're superb metal workers. What we didn't know is they had the mechanical design. And I'll mention that there are a lot of references in literature to such machines. I've been digging around in the literature recently, and there's a guy called Boethius who was one of the main philosophers of the medieval world. You may have heard of him. He wrote a book called The Consolation of Philosophy. Here's a rather nice edition of it from about 1365. He was around 500 AD. And Cassiodorus, who's a Roman secretary, writes to Boethius saying, look, can you supply one of these Antikythera mechanisms, but he didn't call them Antikythera mechanisms, he called them spherai, to the king of Burgundy, please. He'd like one. Look, I know you know all about these things. You know how they work. Can you get one ordered and sent to him? And he described it as it shows how the moon recovers from waning and turning by an invisible mechanism. It's a tiny device, a portable sky, a compendium of the universe, a mirror of nature which reflects the heavens. Pretty good description of this apparatus, wouldn't you think? Something that shows the position of the moon, sun, planets in the sky. This is now 600 years later. The tradition survives. They're still making these things. And indeed, I've got a list of at least around 20 to 25 references in classical literature describing devices like the Antikythera mechanism. So they were known about. Okay, it's just we've sort of forgotten that they had these things. Or what's more likely is people reading the classical text have tended to say, well, they said they could do that, but of course they couldn't. Big mistake. Okay, yes, they could. There are other things as well. This is a Byzantine sundial made about 500 AD, about the same time as Cassiodorus was writing to Boethius. A simpler device with 6 gears in. And there are 1 or 2 devices exist between as time goes on. Here's from an Arabic manuscript around 900 AD. Okay, we're jumping forward now 1,000 years, but there's still diagrams of these things. Here's a lovely astrolabe with gearing in, which comes from, it's in the Museum of the History of Science in Oxford, from around 1200 AD. And that has a sort of astronomical display mechanism in, shows the phase of the moon and where the moon and the sun are in the sky. Not very accurately, but it's a beautiful device. I had a good play with it last year. It was great. Okay, again, quite nicely made. And we're moving forward, and suddenly, around 280 AD, somebody discovers the escapement. And the escapement is the mechanism that allows you to have mechanical clocks. It's not the pendulum. You might think the pendulum is the first thing. That doesn't come along till quite a bit later, 16-something or other, by Huygens. Now, an escapement was a thing, I'll just demonstrate it. You can see it here. It's a sort of shaft with a sort of thing on that does this. Tick, tock, tick, tock. And that releases, by little pivots on this wheel, or little vanes on this wheel, the crown wheel can click round, click round, click round. It's a regular oscillator. And that, the first time, allows you a proper mechanical clock. It was invented in 1280. Nobody knows where or by whom, surprisingly. But they know it was done within probably 10 years of 1280. And once that was invented, clockmaking just exploded across Europe. And all sorts of people start making astronomical clocks and ordinary clocks. Richard of Wallingford, who was the abbot of St. Albans, he left a manuscript with some details of how to construct a mechanical clock, looking very much like some of these bits like the Antikythera mechanism. Classic among this is a guy called Giovanni De Donde in Italy, who around 1364 made a clock, and in fact published a manuscript, or left a manuscript, which exists in many copies, showing how to construct the damn thing with 107 gears. And there's a reconstruction of it. Beautiful thing, about this high, with dials showing the sun, the moon, planets, and so on. This is the first thing. There is another reconstruction. The first thing, we're now 1365, the first thing we know about that was more complicated geared mechanism, the Antikythera mechanism. Okay. Now, gear wheels are evolving. Before this time, before about 1300, they're little triangles. They're just teeth, are little equilateral triangles. Beyond this time, you get much more complicated, better teeth forms. And if I look forward again, I'm only going to be about 10 more minutes at most. If I look forward again, about 200 years again forward, from De Donde's clock to Kepler, my aim is to show that the heavy machine is not a kind of divine being, but a kind of clockwork. Now, you've all heard of Kepler and the planetary system and so on. Kepler took seriously this idea, or had some notion of taking seriously the idea of the universe as a clockwork thing. And as I say, before him, there's the era of the great astronomical clocks from 1300 to 1400. Here's some pictures. They didn't necessarily display the planets, but would often display the sun and the moon and the positions in the sky during that time. And leading on later on to the orreries, these planetary models. I couldn't resist putting that one in, or this one here around 1800. Now, back to our problem here, which is this is a computing conference. So, you've seen this device. The Antikythera device, and some of these others, are calculators. They're pre-programmed, they're not programmable, but they're pretty good calculators. They do multiplication, they do division, essentially. Now, was it possible that even in the classical era, they produced mechanical calculators, more general calculators? And we know they had sort of counting boards and abacuses, that's Greek, that's Roman, but could they have produced a mechanical calculator from that, using the technology of the Antikythera mechanism type machines? Now, I did a bit of work a couple of years ago looking at how accurately the gear wheels were cut and made. And you can then, if you work that out, you can then do experiments where you build, in the computer, of course, you build models with those gear characteristics and ask how accurately could you make a calculator? And the answer is you can do not badly. The Antikythera mechanism would have worked reasonably well. It might have been a month wrong in some of its eclipse predictions. It might have shown the moon 20 degrees away from the sky from where it was, but it'd be approximately right. That's fine. However, if your bank balance was 10 drachmas wrong because of an error in the computer, you wouldn't have been very pleased. You're not pleased these days when it happens. And I think the actual technology of the Antikythera mechanism was such that it couldn't be very, very accurate. And for financial computing, that would probably not be sufficient. They had slaves. They had a lot of people doing calculations. They had a lot. The Romans certainly had a vast amount of administrative calculations in surveying, in finance, in goodness knows what. They'd have loved something like this, but they didn't seem to have developed it. Maybe it's because they just had enough people they could use to do the calculations. It would only have been a small step, however, to add some sort of click-over device to make it digital, essentially, okay, in order to make these things into fairly reliable calculators. And in fact, they did design some things called hodometers, which are devices for measuring distance, where they did have essentially a click-over device, or hedging towards it. But for some reason, they never put the two together. And looking for computing, we have to go forward quite a long way. There were sort of devices for doing computing in the Middle Ages and onwards, so-called Equatoria, particularly for astronomical computing, but they weren't geared devices. They used sort of wheels and indicators and things. There's one there. Here's a brass one with a sort of a little thing that rotates as you move this around to do various calculations. But they're not geared general purpose calculators, but they are calculators of a kind, but not. I'm going for geared calculators as being real computer type stuff. And in fact, you have to go forward. The first known reference I know to this is a guy called Wilhelm Schickard, who lived in these dates. And he wrote a letter to our friend Kepler in 1623 describing a possible device for doing mathematical operations, sort of arithmetic. And here's a reconstruction of it. It didn't get very far, but they did talk about it. It's the earliest reference I know to a true mechanical computer. However, by 1642, Pascal, who you may have heard about or groaned about in mathematics classes before now, did make one, and it led on to a sort of almost commercial thing called a Pascaline, a kind of calculator, around 1642 that worked, but it was quite complicated, as you can see. Again, it was never really commercialized, largely, a bit, but not much. And here's a lovely one I like, which is by a guy called Samuel Morland, who was United Kingdom, invented in 1666. This is a little adding machine, little pocket adding machine. And in fact, he wrote about it and said, here we are, invented, humbly presented to the king, Charles II. He actually presented it to Charles II. And here's a description of how it worked. But these, again, were sort of demonstration devices, but not particularly commercial devices. And it wasn't until later on, and I have to mention Babbage here, I guess, that things really got going as far as mechanical computing. It was really the 19th century before things really got going in mechanical computing. And interestingly enough, I discovered, in fact, that one of the main things that drove Babbage into the ideas of computing was, in fact, again, astronomy. Okay? It's astronomy because there was a vast need for tables, or what were called the Nautical Almanac and Astronomical Ephemeris, particularly for surveying and for navigation at sea. They needed positions of where all the sun, the moon, and the planets were accurately, and they had reams and reams of tables that had to be calculated. And the computers then were people. They had people who were employed, called computers, who would work out these tables. Be thankful you don't live in those days anymore. Otherwise, we'd be just training you to, write out longhand things right. And Babbage realized that he thought he would like to do this mechanically for two reasons. One, because it would be easier and you could do the tables quicker. And also he believed that doing it mechanically, you could do it more accurately. In other words, one of the problems was, in doing the calculations or even writing them out, they made lots of mistakes. And he was trying to invent a device that would do the calculations and print them at the same time, to sort of take out a whole stage. And he made some progress. And the first thing I know about is 1882. I looked it up the other day. It's rather a bad photo, I'm afraid. 1882, in the first volume of the Memoirs of the Royal Astronomical Society, a note respecting the application of machinery to the calculation of astronomical tables. And that's what he was intending to do. And he invented various devices to do that, particularly his difference engine, as it's known. There we are, nice little pocket calculator there. And as you know, these difference engines and also his differential engines later have been reconstructed. And they're very interesting. He never really got things to work. He was always on to the next thing before he'd completed one thing. Beware, in doing your PhDs, there's always a temptation to move on to the next thing before completing the first thing. Take a note from Mr. Babbage that although you can be very bright, it will not bring your PhD to completion. Okay, and in the 19th century, this is Babbage's difference engine, but they then did begin to make actual viable computers. Tidal prediction was one of the ones they did, which is, I haven't got time to talk about, very interesting, really a Fourier analysis, essentially, by mechanical means. And proper calculated the arithmeter. Here's a one that certainly during the 19th, 20th century was known as hand calculators. An awful lot of science was done using these mechanical calculators. And I might mention, in fact, that I was reading a very nice book, I don't know if many of you know it, called Turing's Cathedral. I don't know if you know this book. It's probably on your reading list these days, by the son of Freeman Dyson, in fact, about computing and the atomic bomb and things. And this is what they started the Manhattan Atomic Bomb Project with. They didn't have computers. They built them during the project and got them going, but they had 10 of these, I think, was their first computing resource. Okay? And if you take one of those apart, it's that. Doesn't that look like the Antikythera mechanism? Okay, there's a sort of complete, a line right the way through there to these late mechanical computers. I want just Babbage was a very clever guy. He did some lovely things. He produced, you may have seen this formula before. I think it was due to Laplace or something. I can't remember, or Euler. A singular formula which produces primes, not all primes or primes, but 40. The first 40 things, you substitute an integer in here, the first 40 of those are all primes. Here's the first 100, the red ones aren't primes. And he did that by a very elegant method of what are called differences. I won't go into the details, but he was one of the guys who really invented algorithms as well, clever ways to do computing when he got doing production of primes and tables just by addition. Okay, and of course, orreries and computing goes on till today. I can't resist showing this is a modern version of a Antikythera mechanism, I suppose. This is produced by the Kepler Project looking for exoplanets around other stars, and they published this on the web as a little mechanical orrery. This would be your modern equivalent to the Antikythera mechanism, I guess. It's rather fun, isn't it? Okay, I'll stop there. Thank you very much.